So, Pythagorean theorem, I don't know why they wait till now to do this, because they've done this a lot, right? But they finally give it to us as a theorem. So again, if you want to make, you want to see the exact words. The most important part of theorem 54 is in a right triangle, right? If I do not have a right triangle, I can never do the Pythagorean theorem. This will be big here when we get into trigonometry and the end of this chapter. Okay. We'll do some trig, well, now next week. So what do we know about the Pythagorean theorem? Okay, now in this case right here, today when we write this, I'm going to write it as this, just because of the inequality that we're going to do here in a little bit. So all I did was flip-flop it basically, right? It's still the same thing. It's just I wrote the answer first instead of the problem. And so then we would know that this is any side or any two sides of a right triangle. If you square those sides and add them together, they should equal the third side, which is, my C is always my what again? This has to be my hypotenuse, which is the longest side. And I always know that it's the longest side because it's opposite of the box, or 90 degrees. Exactly right. And again, that's another key thing that you really got to take to heart here, is when we say opposite of, it means like diagonal from. And that's going to be really important when we get into trig and that kind of thing. Okay? So again, if you really wanted the words, they said the sum of the squares of the measures of the legs equals the square of the measure of the hypotenuse. Okay? From there then, they introduce something, and I always get yelled at because they say I never teach this, and I always know that I do, but it's always an argument. A Pythagorean triple. Any idea what a Pythagorean triple means?
Three values that show the triangle is a right triangle.
Is it when, like,
Essentially.
is it that A and B equals a perfect square?
Right. So Pythagorean triple is just the three numbers that work in the Pythagorean theorem. So, what is a Pythagorean triple? 3, 4, 5 works, right? Does 6, 8, 10 work? Oh, you're looking at the book.
So don't they, like, the
Okay.
first one?
So this is the three sides. Obviously, you would know that which side would have to be the hypotenuse. The 5, okay? The next one that comes up a lot is 12, 13, and 5. Okay? Every single time, you know that that's going to work. But now, so you can carry this further, and this is kind of what Mr. Rulin is getting at. If I squared each one of these numbers, or if I cubed each one of these numbers, they would also work. So if I took this and squared this, then I'd have 9, 16, and 25. Those should also work in a Pythagorean triple. See what I'm saying?
And if you add those first two, don't they have to be bigger than the hypotenuse to be Pythagorean triple, or what? How do you know?
No, that just tells you that they do make up a triangle.
But if you can square them equally, that's what you're saying.
So how do you know?
Practice.
What?
Well, I would know that this is a Pythagorean triple because if I did 5 squared plus 12 squared, it's going to equal 13 squared. So 5 squared is 25 plus 144 equals 169.
Okay.
These are the three numbers that go into Pythagorean theorem.
So if I square and add those together, they should equal.
But if I square them, so if I took all of these and squared those numbers, another Pythagorean triple would be 9, 16, and 25. So you could prove this. If you took 9 squared plus 16 squared, it should equal 25 squared.
And if it does,
Then it is a Pythagorean triple.
so you basically plug it over.
Yeah, you're going to take those three numbers. So anytime that I see 5, 12, and 13, or multiples of them, they'll work. So if I would square each one of those, they would work. So 25 plus 144 equals 169. Okay? So Is it really important? Well, no, but those are the little things. And there's a chart that Mr. Shetler was trying to sound smart about on page 548, if you actually want to see some of those other ones. Okay? So those are just things that would come up, maybe on that ISAS test coming up and stuff. Those are things that might show up. So then theorem 8.5 is basically the converse of. What have we learned about the converse of?
Opposite.
It's the opposite. It goes in a different direction. So converse of the Pythagorean theorem. And again, so the words say, if the sum of the squares of the measures of two sides of a triangle equals the square of the measure of the longest side, then it is a right triangle. So this is saying in a right triangle we can do this. This is saying that if we actually do the math and it works, then it is a right triangle for sure. So they would just give you some numbers in this one. And they would say, if I had 7, 10, and 14, for instance, is this a Pythagorean or a Pythagorean triple? So that's what they would say. Is this a Pythagorean triple? And I could use this. So is 49 plus 100 equal to, what was 14 squared?
It's not equal.
It's
It's
not.
not going to equal, right? What was 14?
13 is 160.
196. So does that work? No. So the converse of this is saying this is false. Okay? And then if we would have done this one right up here, 5 squared plus 12 squared equals 13 squared. Is that true? Yes. And it's true because of the converse. Okay? That's all that that's saying. So one's telling you that it is a right triangle. The other one's telling you, do those numbers form a right triangle? Okay? Which leads us to inequality theorems. So when we think about Pythagorean inequality theorems, this means that basically we're going to have a problem where we're going to have an inequality symbol in the problem. That's all that that's saying. So in theorem 8.6, it's saying this. And if you notice up here, on the notes up here, I said, I would always try to do this section at least in this form right here. Meaning, I'm always going to put the answer first, or the hypotenuse first, and then equal to. Because when you get to this, it makes more sense to me to do this than it does our normal way, which is a squared plus b squared equals c squared. Okay, so theorem 8.6 says this. If the square of the longest side or another way, longest side of a triangle is less than the sum of the squares of the other two sides the triangle is acute. So basically, if we came back to this one right here, all right, I always know that my biggest number has to be the longest side, right? So if I did this problem right here, and this is where, if I switched this and I said 196, and then I left kind of like a box or something to fill in there, and I asked you, what would I fill in with that problem right there? So if I did the math over here, 49 plus 100 is obviously what? 49 plus 100 is 149. So is 196 compared to 149 is what? Is greater than. Okay? Does that say what this says? Is the square of the longest side of is less than the sum? No, it was greater than, right? So it's not acute. So that leads us to theorem 8.7. So 8.7 just says the exact same thing, but put greater than here. So if you want to copy the whole thing down, otherwise change less than to greater than in theorem 8.7. So if the square of, I'm going to get really lazy and say longest side of a triangle is greater than the sum of squares of other two sides. The triangle is. So if it's greater than, we would say then the triangle is what?
Obtuse.
Is obtuse. And everybody good with those two words? What does it mean if my triangle is acute? What?
The C angle is less than 90.
Just the C angle?
All the angles.
In an acute triangle, all the angles are less than 90 degrees. If it's an obtuse triangle,
The C angle
it doesn't matter about what angle it is. Okay? Because if it's an obtuse triangle, that C would actually be opposite of what? The longest side, or the longest angle, biggest angle, and it's got to be greater than what if it's obtuse? 90 degrees. So when we're talking about originally C squared equals A squared plus B squared, this right here isn't necessarily talking about a right triangle. These two aren't. This one is. So that's why if you do it in this manner right here, where you do the answer is and then leave a box to the other two sides, you can fill in that box with equals to, and then you know it's a right triangle, less than, and you know it's an acute triangle, and greater than, and you know it's a obtuse triangle. And that's basically what they're going to do. Okay? So, we can do this as simple as this right here. If we do 11, 60, and 61. Now don't just jump to the conclusion that it's going to always kind of be in a glamorous order. So I'm going to say 61 squared is equal to, and then the other two numbers were 11 and 60. Every single time I'm just going to put it into that equation right there. And sorry, I don't want to put equals. I want to put a box or a circle or something to fill in. So if you did the math, if you punch this into your calculator, is 61 squared equals to, less than, or greater than? Equals to. So if it's equals to, what kind of triangle do I have?
Right.
So this is a right triangle. Make sense? Now, the one that kind of gives people problems is this one. 2 square root of 3, 4 square root of 2, and 3 square root of 5. Why does this one give people problems? They really don't know which one's the biggest side. So again, don't just jump to the conclusion that this one right here is the biggest side because it's the third side given. So realistically, you should punch all those into your calculator and see what they are as a decimal, if you don't know.
So for this method, could you just square each one and then we'll put 2 times, probably 4 times 3?
You're right, you're going to square them to still do this, but you got to know which one is your biggest side. Because, well, you can do it afterwards.
If you square it first.
Right.
If you square, you just figure it out.
If you square it first, then you can know what they
Because then you can do 2 times or 4 times 3, then. Something like that.
Yeah.
Because you break it out.
Yeah, but when you square this, when you put these into this equation right here, you need to square both of those terms.
Yeah.
Yeah.
So did that person.
Well, what I'm saying, so you could do that as long as then when you get your answers to all of them,
You said
You use the
then you know that you're going to come back here and put it into that.
Okay.
So after you do that, you just rearrange them in that same type of order?
Right. Then after you do that, then you would put your biggest term here. So basically, what Brandon's saying is he wants to square this, and square this. And that's totally
Well,
fine.
then, can't you go to like where the 196 is and just use those numbers? Like use the numbers that you get from there.
Right, but I still have to know which one's the biggest.
Well, it would be the biggest. If you square them, one the biggest one is.
Right, I'm just saying that because they wrote them this way, don't just always assume that this is the
Oh,
biggest.
yeah.
Okay, so if I square this, what do I get?
3.5.
How about 12?
12, yeah, because you go.
Oh, square, yeah, square. I was actually doing like the actual.
And if I square this one, I get what?
632.
4 squared is 16 times 2 is 32. And this one?
45.
So they actually did give it to you in the right order. See what I'm saying there? So then, if you do it that way, then when you put it back here, you're just saying, is 45 equal to 12 plus 32? You don't have to square it again then. Okay? So is this true or false? Or, sorry, again, you don't always I put an equal sign in there, but I'm going to put a box in it, right? Is 12 plus 32 45? So it's 44. So 45 is what? Greater than. So if it's greater than, it's what? It's an obtuse triangle.
So what if you do it?
So we were saying the same thing. We just kind of
What
said
if you're doing
Yeah.
it normal way?
what's the normal way?
That is the normal.
He's talking about making decimal choice.
If you're going to make them decimals, you're going to do the same thing, but it's probably more work than what these two guys are doing.
Yeah.
Because then you just don't want to round that decimal to the very end. Now, in this case, it probably wouldn't have mattered. Well, yeah, it probably would have. Because if you rounded this and then you got this to be 45 is equal to 45 because you rounded wrong, then it turns into a right triangle where the others had an obtuse triangle. Okay? That makes sense? Everybody good? So, again, just be careful, and I know once in a while, maybe the quiz or the test, I don't put them in the certain order. Okay? I really don't think.
What would you do for, well, we're back, the last one?
Square both sides.
But,
Oh, okay, so this is just another problem, right? Come on. So this is basically, anytime that I have something like this, we're going to try to solve for x, right? So basically we're doing inverse operations. Again, we're working through PEMDAS, and we're doing inverse operations. So this is just solving a problem. So if I have this, I'm trying to get x to be all by itself. Well, what does it mean on this right-hand side between all of those terms? I'm going to multiply all those things, right? So the first thing I'm going to do is divide by 3. And my 3's cancel out. I'm left with x times the square root of 3. Over here I get 6. Now I'm going to divide by the square root of 3 because I want x to be all by itself. And so this is why we talked about that, or those problems in the review section at the end of the last section. Remember, this is called rationalizing the denominator, meaning you can never have a radical in the bottom. So anytime that I have a radical in the bottom, I'm going to multiply another fraction of that same radical in the bottom and the top of a fraction. And why can I do this? Because if I make a fraction of anything, as long as it's something over itself, that's 1, right? And so then, here's where a lot of people make the mistake of, if you're multiplying fractions, one of the first things that we usually say is you can simplify diagonally. Well, if you simplify diagonally, what happens? You actually go right back to what you had. So when you're rationalizing a denominator, don't look diagonal to cancel out. Now just multiply straight across the top and straight across the bottom. So on the top, here again, remember, I can only do the insides times the insides and the outsides by the outsides. So this one's outside of the radical, this one's on the inside. They just come together then. Down on the bottom, what's a radical times itself? That number, but it gets busted out of that radical. Now here's the question of the day for this problem right here. Don't say it out loud, let everybody have a chance to think. Can I cancel anything out right there of that fraction? See how all of them are basically have a multiple of 3 of them? Can I cancel all of those out? Everybody agree that it's no? Can I do anything?
6 and
Yeah, see how the numbers that are on the outside, I can reduce them, so I can take 6 divided by 3, which is 2 square root of 3. But again, I can't go underneath the radical, because it's basically kind of like a shell, and it's protecting that number on the inside. So this right here should be reduced to 2 square root of 3.
And that means you don't put them back in for.
Nope, that's my answer. I'm solving, that problem right there just says solve for x, essentially. Yes?
I think I would, can you just square both sides and go 6 equals x times square root of 3, instead of just dividing that square root of 3?
But then you're gonna have x squared.
Yeah, and then just divide by,
Then
it's
you're
gonna
gonna
be 3x,
take,
it's gonna be 3x squared, but then just divide by 3, divide 36 by 3 to get 12, 12 equals x squared, and you just do square root of the answer.
it's the same difference.
I'm just.
You're taking the strip. I would say that's a longer version of it,
Let's be nice.
but you can do it that way. Because you're gonna have to take the square root of both sides, and then you're gonna have to simplify your radical. This is just doing it in, without converting it into a radical, or into a square problem.
Sure.
Okay?
Thanks.
But either way, it should have worked. It should have worked. I don't believe anything else. So again, here's a real simple problem. The only thing that you have to remember is which one are they giving me, right? So in this one, what don't I know? I don't know C, right? Okay, so again, same thing with that one. They just asked you to use Pythagorean triples. And then basically they're just showing you that you could use this again in real world situations. A 20-foot ladder is placed against the building to reach a window that is 16 feet above. How many feet away are the building from the bottom of the ladder? So if Gabriel wants to be safe when he's climbing up to rescue his damsel in distress, he would have to figure out how far to put his
He's cool, man.
What if, can we, pick up the last one, if it's like 4 squared plus 7 squared equals x squared? So it'd be.
what?
He's talking about the
Problem
first
there,
example.
The first example.
The very first one?
Yeah. Well, the first one that you showed us, I don't know which one it was.
That one.
Yeah. It turns into like 65 squared, and can we just make that into a decimal? Or do we have to?
Oh. Good question. I would not do anything with the decimal. I'd leave them all as radicals.
So I don't have to.
Do more.
So yeah, you're right, it's the square root of 65. Then I'm gonna see if I can simplify that. Okay? Again, the only reason I say that is if you want something to be exact, the square root of 65 is better than you rounding the decimal. Alright? And then I believe the only other ones, just like the ones we had. So, is 9, 12, or 15, do they make a acute, right, or an obtuse triangle? So again, we're so used to doing a squared plus b squared equals c squared. Again, I would tell you that if you do it this way, this makes more sense to people saying if that sum is less than, then it's acute. If you do it the normal way, then it's really backwards of what you're saying. You just have to read it backwards.
Right triangle.
This is a right triangle?
So does these are all back, would you not, otherwise it's all back?
If I divided by 3, and then I would go back to that 3, 4, 5,
Yeah.
and that's a Pythagorean triple, absolutely. So you can square them, you can multiply them by the same numbers, it doesn't matter. If it's originally a Pythagorean triple, all of those things will be true about that. Okay? Questions? Okay. Tomorrow I think we finally get into the fun stuff. Not that this isn't fun.
Like sign.
Like perfect squares. No, not perfect squares. Tomorrow is